I said we were going to return to the example of looking at these two functions, the squaring function and the square root function, which we know are not inverses of each other. We know that for several reasons. First of all, we have determined repeatedly that this function, the squaring function, is not invertible because it's not one-to-one. Okay. Second, when we were looking at composition of functions, we saw that if I took f of g of x, I did get just x, but if I took g of f of x, I got the absolute value of x. And I said that was kind of interesting, and it had something to do with the domains and the ranges of our functions. Okay. So before I get to addressing that directly, I want to just look at g of x. Is this function invertible? I know that one isn't, but is this one? Yes. It definitely passes the horizontal line test. No horizontal line intersects the graph more than once. In fact, when we talked about the horizontal line test, we said that if our function is defined on an interval, and here my domain is the interval from 0 to infinity, including 0. If we're defined on that interval and we're always increasing on that interval, same would be true for decreasing, but this function is always increasing, then we're going to have a one-to-one function. So this function is one-to-one. It is invertible. But I know that function is not the inverse, because that function isn't invertible, and inverse functions come in pairs. Okay. So what I'd like to do is try to find what the inverse of g is. So I would first of all write g just using y's and x's. So I'd say that's my original function. Excuse me. Y equals the square root of x. Then I would switch the roles of x and y. So we get x equals the square root of y. Now that's going to be my inverse function. Okay. And then to get y by itself, I would solve for both sides. Or not I would solve for both sides. To solve for y and get y by itself, I would square both sides. I'm sorry, I misspoke. Now it looks like I'm getting y equals x squared. But I need to take a look. I had some information encoded in this equation here that got lost here. Okay. Here, y could not be negative because otherwise I couldn't take the square root of it. Now in this equation, I can still see that y can't be negative because x squared will never give me a negative number. But in this equation, x was also not negative because the result of taking the square root of something is never going to give me a negative number. But in this equation, it looks like x could be negative. Anytime I do something to change an equation, if I lose restrictions, I need to explicitly record them. So, my inverse function is not the squaring function, but the squaring function with this restricted domain. So I would say g inverse of x is the function x squared with the restriction that x is bigger than or equal to 0. Okay. That is part of that definition. Now if I take a look at what that would look like, that's just going to be the right half of my parabola. If I restrict the domain and I get rid of the left half of the parabola, now I've got an invertible function. We will see this later this semester when we get to inverse trig functions. We're going to have functions that, just like the squaring function, fail the horizontal line test. And we're going to create new functions by restricting the domain so that we're working with just a portion of the graph so that we pass the horizontal line test, and those new functions will be invertible. Okay. So how does this tie in with the notion of the domain and the range? Well, if I look here, g of x, we said the domain was everything from 0 to infinity. The range is also everything from 0 to infinity. I'm getting just non-negative y values as well. And the rule is, because inverse functions, we're just switching the roles of x and y, the domain of G is equal to the range of G inverse. And the range of G is equal to the domain of G inverse. So the reason that x squared and the square root function were not inverses, or one reason that they weren't inverses, is because they did not satisfy this rule. When I take this function and I invert it, the range that I'm starting with is just non-negative numbers. That needs to become the domain for my inverse function. And that really makes a lot of sense because the domain is just the set of all x values. When I take the inverse, those become my y values. And the range was just the set of all all y values. When I take the inverse, those become my x values. Okay. So that's nice. And if you have a pair of functions and you can see that that relationship is not satisfied, that's going to tell you they can't possibly be inverses of each other.